Hello everyone, welcome back to another video for the series. I'm Enoch Yu, and today I brought a problem from number theory. I won't say it's like a problem, but I think proving something is still considered as a problem, so yes, I brought a problem. So today I would like to prove the Euler's theorem. And please note that this is not my proof, so there is a proof for this and I just wanted to introduce it. I saw other proofs using I forgot how to pronounce this mathematician's name. I first thought the way to pronounce this name was Lagrange, but I think it's Lagrange. Like multipliers and stuffs, and that was quite complicated because using abstract algebra is quite complicated when we use abstract algebra. So I wanted to introduce a method that uses just basic properties of modular arithmetic. And after I prove this, I would like to also prove its corollary, Fermat's little theorem. Okay, so before I reprove this, let's define it first. So for all a comma n equal 1, so the greatest common factor of a and n is 1. This is Euler's Taussian function phi is congruent to 1 mod n. And I think this theorem is used a lot actually, but I was not able to see its application in Olympiad problems yet. Maybe I just didn't study enough, but I'm pretty sure, I'm 100% sure this comes out in AMC because I saw this in AMC 12 problem 20-ish, maybe 17. So I'm pretty sure it comes out in AMC, but because I didn't study enough for Olympiad, I'm not sure about that. But one evident application is wait, let me think of a good example. Find the remainder when 3 to the power of 16? No, 17? Yeah, 17. No, because yes. Okay, I'm almost done. Okay, 800 and okay. Is divided by 17. And here's the solution. Also, because I just created this problem, if you think I made a mistake, please feel free to let us know in the comment below. So we know that because we know that this is true, and I'll just write because here quickly. Because equals 1, 3 to the power of phi of 17 is congruent to 1 mod 17. And when we calculate this, because it's a prime number, it's quite simple, I think, like this. Oh, and using the basic properties of modular arithmetic, we know that this is congruent to 1 mod 17. Therefore 81, right? Mod 17, which is equivalent to 9 times 9 is 81. 17 times 5, 4. So 13. Yeah, I need to double check quickly. Yeah, I think it is, and it is indeed right. Okay, so our answer is 13. Yay. And I think this is one evident example And I think this is really useful. Yes. Now, because we know how to use like Euler's theorem, let's prove it. This proof, before we prove it, we need to define Euler's torsion function. So phi of n is equal to the number of elements in reduced residue. Oops. Residue of a residue system of modulo n. So what this means is like, okay, we have we can write every numbers until n minus 1, and we're going to choose every element, every numbers that are co-prime to n. That is like the residue or reduced residue system of modulo n, and we're just finding the number of it. And there's a good formula for it, but I'm not sure if this is used in the proof. So, and I'm pretty sure it's not used in this proof. So I don't think I need to, like, we need to talk about that here. Okay, now that we defined this, yes. First, let's write the reduced residue system of n. I'm not sure if this is most people like use this notation, but I'm not sure if this is mathematically accepted. But I think it's like generally accepted. Most people use this. That let's just say that this is equal to a sub 1 comma a sub 2 all the way up till a sub n. Oh, sorry, a sub k. Now, let's say that there are k terms. Then we know that this is equal to k, simply. Now, because this is the reduced residue system, assuming that a and n are co-prime to each other, we can rewrite this in like by multiplying it. It doesn't change the fact that it is the reduced residue system of modular n. So because these numbers are congruent to each other, like this one in modulo n. So that's why we can rewrite it like this. Okay, so because we know that this is true, then we also know that when we multiply everything, so 1 times a sub 2 times a sub k, all the way up till a sub k is congruent to, because like the very reasoning that I just explained, times a sub 2 times a sub k mod n. Okay, now how many a's are there? There are k a's here, and then times a sub 1 a sub k is congruent to a sub 1 a sub k mod n. Now remember, we define a sub 1 through a, or we define a sub I as the elements in the reduced residue system of modulo n. That means those numbers, so a sub I and n are co-prime to each other. Therefore, a sub k is congruent to 1 mod n. And what was k? That was phi of n is congruent to 1 mod n, assuming that this one. Assuming that or if a sub, and we need to include this condition because we use that to prove our prove the theorem. So we just proved it. Now there's actually one more good theorem that, like this, the direct consequence of Euler's theorem. So Euler's theorem states that if these two numbers are coprime to each other, then a sub p of n is congruent to 1 mod n. Okay, now let's think about when n is a prime number. So if n is a so that's a fact that we know, and I will write our, wait, is this how I spell it? Yes. It's called Fermat's little theorem. For all prime numbers, I'll write them more legibly. Whereas P and like P and a number A such that P does not divide A to the power of P is congruent to P mod P. So let's prove it. Actually, usually this is like, I don't know why, but like the formal definition, like somewhat formal definition use this one, but I like to use this one. And many people actually use this form too instead of this one. So, but I mean, yeah. Okay. So because P is a prime number and P and A are relatively prime to each other, because A and P are relatively prime to each other, by Euler's theorem, A to the power of phi of n is congruent to 1 mod P. And I miswrote that. Now, what is the reduced residual system of P? It's just simply P minus 1, because like literally every number that is smaller than P will be relatively prime to P. So therefore A to the power of P minus 1 is congruent to it's A. I'm so sorry. Yeah, because I don't usually use this one. I like to use this one, but yeah. So A to the power of P is congruent to A mod P, and we just proved it. Nice. Yeah. So it was Fermat's little theorem that came from Euler's theorem. I really love these theorems because there are lots of things that I think we can do with these theorems and results. So maybe in future videos I might make a video about Lagrange multipliers and Wilson's theorem. I think Wilson's theorem is like another really famous theorem in modular arithmetic, like almost like the same level as Euler's theorem. So yes, maybe I will make a video about that maybe in the future. So I hope you enjoyed this video, and if you did enjoy it, please feel free to share it with anyone who loves math. And thank you, and see you tomorrow. Bye.